Lagrange multipliers, one constraint, right? So what's del f? Del f is equal to, take the, okay, the I component's going to be the partial with respect to x, of f with respect to x. What's that going to be? yz, so yzi plus partial with respect to y, xzj. I like these ones with patterns. You don't really have to think after you see the pattern. And then everything but z, right? So xy, okay. You buy that? And then technically g would be what you get when you subtract the 9, but when you take the partials, that constant of negative 9 will go away. So I'm not going to worry about it. Del g is going to be what? 6xi, leaving space for the lambda, plus what? 2yj plus 8zk multiplied by mu, or let's do lambda here. Lambda. All right, okay, remember what we do. Del f is equal to lambda del g. This is really a system of equations, you guys. When you set one vector equal to another, and you've got variable components, it's really a system of equations. It's a compact way to write that. So we're going to set up that system longhand. And so what are the corresponding components that are equal to each other? yz equals 6 lambda and then x. What's the other one? xz equals 2 lambda y, and then finally xy equals 8 lambda z. And then don't forget your constraint equation, 3x squared plus y squared plus 4z squared equals 9. What is that thing? What does that thing graph to be, that constraint? An ellipse. It's an ellipsoid. Yeah. I like an elliptic sphere. That's interesting. That's what it is. That's what an ellipsoid is. It's a stretched out sphere, right? Or that's one way to look at it. Any questions? I saw a hand back there. Yeah. Yeah, and so you have to address that case when it could be 0. Otherwise, you're dividing out one of your possible solutions. So in this case, could it possibly be 0? Like if it wasn't 0 for everything. Well, that's actually a good observation. So why don't we say that, and then we can start dividing by variables if we address it. So let's address it right away. So I would just say something to the effect that if x, y, or z is equal to 0, what's the function value? 0. No. If x, y, and I'll put an or in here, or z equals 0, then I'm just going to put f is equal to 0. Because f is x times y times z, right? If one of them is 0, if one of those factors is 0, the function value is 0. So now that we've addressed that, let's look at what happens when none of them are 0. Let's assume none of x, y, and z are 0, and then maybe that can help us solve the system, right? In a nice way. So let's assume x, y, you have to change to and here, and z are not, if you want all of them to not equal 0. Okay? So why do we care? Why does that help us? Is it going to help us? I don't know, but it's a good technique to use if you can use that to your advantage. So let's now, I haven't even examined our system. So what have we got here that's interesting? So, yeah, no, I think one thing we could do is solve each of these first 3 equations for perhaps lambda. Does that make sense? I think that's what I'm going to do. That's the first idea that pops into my mind. So here's what I'm going to do, just to organize a little bit and make some room here. I'm going to put this statement up here so I've got plenty of room down here. Okay, so lambda then, again, since we've shown x is not equal to 0, it's okay to divide by it. What do we get? Lambda equals y times z over 6 times x. And that's from the first equation. From the second equation, lambda equals xz over 2y. And from the third equation, xy over 8 times z. Now that's what my instincts are telling me to do. If I feel like, if I work on this for a while and it doesn't go anywhere, try something else, right? Okay, so since all of these things are equal to lambda, the right sides are equal, right? So we get y times z over 6x is equal to x times z over 2y is equal to x times y over 8z. So if we just take two at a time, what can we say? If we set like these two equal. Yeah, so the z's will go away, right? Let's start with that. So y over 6x is equal to x over 2y. Does everybody see what I did there? And then we could manipulate that further. We could cross multiply, couldn't we? And then what would that get us? 2y squared equals 6x squared. And then what else? Y squared equals 3x squared. Now, I like that. Why do I like that? I see a 3x squared in this fourth equation. And I could just replace that thing with y squared. That's pretty. It's almost as if somebody designed it that way. All right. You might imagine that if I just haphazardly put functions together, we could get some pretty ugly, I mean, much uglier systems than we have here. So yeah, I like that result. Now, let's look at this other relationship here. And so that's x. Well, okay, right away, what could we cancel out? The x's actually, right? So we could do that, right? And then we get z over 2 times y equals y over 8 times z. Okay, and then if we cross multiply, what do we get from that? 8z squared equals 2y squared. And if I divide both sides by 2, what do I get? 4z squared equals y squared. That's nice too, because I could replace this guy with y squared. Yeah, well. So all I did was work backwards to create this. When you make problems and you want to make them fairly nice, you have to come up with the answer first and then work backwards. So does everybody see what I'm going to do now? I'm going to replace this guy. I know this guy is equal to y squared, so I'm going to replace 3x squared with y squared. I know this guy, 4z squared, is equal to y squared, so I'm going to replace 4z squared with y squared, and then I have y squared plus y squared plus y squared equals 9. So what's that, 3y squared? Whoops. 3y squared equals 9. Does everybody see that? Or y squared equals 3. So what does y have to, do we care about, yeah, I guess we do. What does y have to equal? Plus or minus root 3. Okay. Now, okay, we have to be careful here. So before I go to this step, if we know y squared equals 3, what does that say about 3x squared? Well, 3x squared equals y squared. So 3x squared would equal 3, right? I mean, yeah, you're ahead of me, but yeah. Right? Does everybody see that from plugging in this guy? Replacing y squared with that guy? And then what else? 4z squared equals 3 as well, right? So the reason I collect these results together is to emphasize the fact that when we take, eventually we'll take the square root of both sides in each one of those equations, right? But because it's the squared variables that matter here that we get this relationship from, we can mix and match the pluses and minuses, right? So my point here is, okay, from this guy, I do get y, as I said before, I get y equals plus or minus root 3. From this guy, somebody already said it, we get x equals plus or minus 1, right? Because you divide both sides by 3, then take the square root, plus or minus. Then from this guy, we get z equals root 3 over 2. There you go. Okay, root 3 over 2. But the thing is, you can mix and match these pluses and minuses, can't you? So I'm just going to say it this way. Actually, I did it in class with a similar one. You could write all, there's 8, there are going to be 8 of them, right? You could write all 8. It wouldn't be that hard. So what would be a convenient way to write all 8? You could write 4 and 2 in each one. So it'd be plus or minus 1. And then I would use for the y, let's say root 3. And for the z, let's say root 3 over 2. Does that make sense? So there's 2 points right there. And then plus or minus 1. Let's go with negative root 3 and positive root 3 over 2. There's 2 more. That's 4, right? And then what else? Plus or minus 1, negative root 3, negative root 3 over 2. That's 6. And then what's the one or the 2 I forgot? Plus or minus 1, root 3, and then negative root 3 over 2. So there's all 8 of them. Would you buy that? Okay, are we going to need to actually compute the function values of all 8 of them? So remember what the function is. Hold on, let me take the long view here. The function is actually x times y times z, right? So you're going to get a positive value when either when all of them are positive, right? When all x, y, and z are positive, that'll definitely give you a positive function value. When else? When 2 of them are negative, right? And then in the other cases, when an odd number are negative, you'll get a negative value. But absolute value-wise, it'll be the same number every time, won't it? So, yeah, so they'll be opposites of each other. And I think that's pretty clear. So we'll just say f. So there are I should make mention, okay, there are 2 unique function values. Okay, f, I'm not going to put the of what because I don't want to do all 8 of these. It's a waste of time. F would equal what? Let's do the positive one. So we could just take 1 times root 3 times root 3 over 2. And of course, any combination of 2 of these negatives produces the same value. So what is that? 3/2. Okay? And then, or f equals, I'm not even going to do it, just negative 3/2, right? So this guy's the absolute max. And this guy's the absolute min.